I'd like to introduce the salesman traveling problem. The salesman traveling problem is one of the most famous applications in the neural network. Based on the name, you can tell the salesman traveling problem is about a salesman. So assume you are a salesman. So your job is to visit the different cities and sell your product. In this example, you plan to visit 4 cities, and they are Indianapolis, St. Louis, Springfield, and Chicago, 4 very big cities. So between these 4 cities, there are highways connecting them together. Here I use different color to indicate different highways. So there are highway between Chicago and Springfield, between Springfield and St. Louis, between St. Louis and Indianapolis. But there's no highway connecting St. Louis and Chicago, because these 2 cities are not adjacent cities and they are too far away from each other. Since you are a salesman, you're visiting these 4 cities for work, not for fun, right? So you want to visit each city for only once. You don't want to visit any city twice. So before you do this work, you need to make a plan, which can give you the shortest route to finish this job. Okay, now let's simulate 2 different scenarios. In both scenarios, you start from Indianapolis. Here I'm using red star to indicate this city, Indianapolis. In the first scenario, you're choosing Chicago as your first stop, and then Springfield as your second stop, and then move to St. Louis. Now you got your work done. You finish visiting these 4 cities, and for each city you only visit once. I will call this is the best plan, because you're using the shortest route and got your work done. Now let's try the second scenario. In this scenario, first, you decide to visit St. Louis. So after St. Louis, you have to go to Chicago, because that is the last city you have to visit. Since there's no highway between St. Louis and Chicago, you either go to Indianapolis, and from Indianapolis go to Chicago, or you from St. Louis go back to Springfield, and from Springfield go to Chicago. But in both cases, you visit either Indianapolis or Springfield twice. Okay? So even you got your work done, but you waste a lot of time and waste a lot of money. Your boss doesn't like you. So let's see, finding the optimal route is the salesman traveling problem. In this example, we only using 4 cities. So you can say, okay, this is pretty easy. It's not a big deal. But think about this way. How about you visit 40 cities? How about you visit 400 cities? That could be an extremely difficult problem. So the self-organizing maps is one of the best way to solve this kind of problem. In this video, I'd like to show you how to apply SOM into the salesman traveling problem. Here we use Matlab code to show this application. Of course, you can use in other language such as Python, C, C++, and etc. So the algorithm is the same, but you need just to follow the grammar from each language. So before write your code, you first need to download the city map file. So here we're using the cities from Uruguay as the example. The file name is uy734.dat. So you can download this file from Blackboard or from a website. If you want to take a look what's inside the file, you can use any editor to open the file. And here I'm using the VI as an example, and let's see, VI uy734.dat. So now we open the file, and basically this is a matrix. They have 3 columns, and the total is 734 rows. Here we're using 734 cities from Uruguay as an example. So on the first column, they are the index of the cities, and the second column is the latitude of each city, and the third column is the longitude of each city. So if you open a Google map and type in Uruguay latitude and longitude map, and you can find the map for Uruguay. So we're using the right one as an example. So here is the latitude and longitude, and here are the cities in Uruguay. And in this example, we're using total 734 cities. So let's see, this is the cities. Now let's back to the Matlab. Here, the first thing is you need to make sure you keep the file and your code under the same directory. So here, let's do first we click the new script. So now you open the editor for your code, and under this new script you can write your code. Here the first step is we type in clean and close all. So this means you want to clean out the memory and close out opening figures. So this is a very important step. You can use CLC, so they do the same functions. Now let's save our code. We click save, and then give a name for your file. We're using the som/main.m as example. Okay, now look at it here. Back to your current folder. There are 2 files under current folder. One is the data file, the uy734.dat. Another one is the new files you just generate, is the som/main.m. Since here we know all the data or all the city information is saved in this uy734.dat, the first thing we need to do is we need to load the files. So here's what we do is we type in the fid equal to fopen fid, then is the uy734.dat. So the meaning of this line is you want to find the file. The file name is uy734.dat, and you give the file into a pointer. The pointer is the fid. So if you run the code, oh no, it's wrong. It's just do this. It's wrong here. Okay, let's look at what's your FID. Now your FID has a positive value. It's 8. So that means if positive value tells you the code can find this file. Let's give another example. If you try the yy734.dat, we know there's no such files. And if you try run this code, click run, and you look at the FID, then give you a -1. That means you cannot find such file. Okay, let's go back to the UI 734, and then the folder, no, the pointer can tells you they can find the file. And then next line we type in is we give like for example the file data equal to text scan fid, and then s. So the text scan can scan out the data from FID into the file data, right? So why there's 3S? Because we know, look at our file. There are 3 columns, so that means we need the 3S. S means string, okay? So we scan the data and save them into the file data. So next step is, since here we open the FID, now we just need to close it. We do the F close FID. Here, let's see, since we save all the text file, the string file into the file data, and let's take a look how long is the file. Let's look at the row equal to length file data. One. Okay, let's look at the file first. If we only look at the file data, if we only look at the length of file data, we don't specifically give it 1. You can see there's 3. That tells you there are 3 lines. And if you try the file data 1, you look at the number of row. Row tells you 734. Okay, that means the file, there are 3 columns. Each column there's 734 rows. And now we define 2 variables. One is called the LLA, equal to the file data 2, and LLO equal to file data 3. Of course, we know here the index is the file data and 1. So let's run the code, and we can check all the values. Index is from 1 until 734, and the LLA, that's longitude. You can see this is all the longitude, and of course the LLO is all the longitude. So here we can see they're using this one to indicate, that tells this is a string. So we need to convert a string to the numbers. So this is what we're going to do is we give another variables, is the for I equal to 0, and give the x equal to string to number, and then using the cell to match, and then give the LLO and I. Similar, we can give define another variable called the y equal to latitude. We save all the latitude into here. And now we can run our code. Let's check the size of the x. Size of x is 1734. Let's save all the latitude. And similar for the y, let's save all the longitude. And then if we want to plot to say what this looks like, we can do the plot x and y, and using red dot, we give the marker size, give like a little bit big, it's 9. Let's see. So here we're getting this plot. So here is plot all the x and the y, and this is their distribution. So here's longitude, here's latitude. And if we compare with the map, we can see let's show you the same thing. This is the latitude, and here's the longitude, and here's all the cities we using in this example. There's total 734 cities. Now we successfully loaded each city's latitude and longitude into x and y. Next step is doing the normalization. Since the range of latitude and longitude are different, this step can normalize them both into range between 0 and 1. Let's see how can we do the normalization. So here we give a new variable called xx. That's equal to x minus x, and then over the maximum x and the minus minimum x. Similar, we can define a new variable called the yy. So here yy equal to y minus minimum y over maximum y minus minimum y. So let's give another figure and plot xx, yy, and using the red star. Let's see what we're going to get. So look at here. Basically, you're getting two plots. Figure. Let's bring back the first plot. And now we have two plots, plot 1 and plot B. So basically, this one is plotting the latitude and the longitude. Here's plotting the normalized latitude and longitude. So they are very similar, but the x-axis are changed, becomes a normalized value. Okay, let's close all these figures. So now since we have the xx and the yy, what we need to do is we have a new variable called the city all, and we save all the xx and the yy into this new variable. So far, we finished loading the data and finished the normalization. And next step, we want to initialize our neural network and some useful parameters. So this is called the initialization. So at here, the first, we set the learning rate equal to 0.8. LR equal to 0.8. In order to remind yourself, give the notation. So here's learning rate is give like 0.8. Then we initialize the number of neural that we are going to use. So here size equal to length xx and 8. So look at here. We give the neural size equal to the 8 times the size of the city numbers. Let's run the code here. Take a look. And let's see the n size. The n size. That's equal to 5872. That is 8 times of your city numbers. So we give the initial learning rate, initial neural size, and then we want to give the initial value of each neural. There's something we need to keep in mind. Look at the city, the size of city all. They are in 2 dimensions. One dimension is their normalized latitude, another dimension is the normalized longitude. Therefore, we need to initial our neural as 2 dimensions. So we define the neural as random n size and 2. So let's look at the n. The size n equal to 2-dimensional, and the total number is 5872. So here the rand, R-A-N-D, this can generate a random value. The values range is between 0 and 1. So look at it here, you can just randomly give any values. It's just a random value between 0 and 1. And give a new variable called the lowercase n. N is the n size. Okay, so far we finished initialize the learning rate and our neural. Next step, we are going to train the initialized neural network. So let's see, training neural network. Here we using an integer II to control the iterations time. First of all, let's give 1000 as the iterations time. And next step, we want to randomly choosing one city as the input. So choose a random city. So how can we do that? So here we using index equal to fix rand 1 and then plus 1. So let's look at this sentence. We using fix random 1 multiplied with 734 plus 1. We using this one to randomly choosing an index. So as we remember, the random 1 can generate a random float number between 0 and 1. So you're using random 1 multiplied with 734. Then here you will have a random floating number between 0 and 734. We're using the command fix to convert the random floating number into a random integer number. That number is between 0 and 733. And then we add in 1. That can give us a random integer number between 0 and between 1 and 734. So let's give a try. For example, first time we type in this, we get in 125, and try one more time is 36. One more time is another number. So every single time we will randomly give a number. This number is an integer number between 1 and 734. We can use this one as an index for the city. So here we give one more, is the city equal to city all and index. So let's see, first time we give a random number index, and then the city let's run this and let's give a try. So the city will equal to this one. This one is the normalized latitude and longitude of the city. And now we can, through this part, we can randomly choosing one city as the training data, as the input. So far, we got everything ready. We can move to the major part of this code, that is the SOM. In this section, for the first step, we need to identify which neuron is the closest one to the selected city. For this purpose, we'd like to create a new function. You click New, and then you open a new script. You can type your function. You can type in your function here. So we type in function, and the winner index, and then it's your function name. You can give any arbitrary name you want. So here we're using select winner, and then it's the NN and the city. So look at this function. Here the input are the whole neural network NN and the selected city. For the output, that will be the index of the winner. So here, for the first step, we need to calculate the Euclidean distance as this. So here, please keep in mind, the NN is a two-dimensional vector and the city is two-dimensional variable. Therefore, the output will be a vector. Let's take a look. Let's look at here. The distance is a vector. So now we need to figure out which one has the minimum value. We using the Matlab function for the minimal value. So here the MIN is a Matlab built-in function that can find the minimum value for a given vector or given matrix. Let's take a look. The winner distance is equal to this value and the winner index equal to this value. Then let's go back to here. Since now we can save the code, we click save. That can save this function. So here it's automatically save the function name as selected winner, and you click save. And then go back to your main code, and you just copy here, back to the main code. Now you finish the first step in the SOM. The next step is updating the weight of neural. As we introduced in previous video, we know not only the winner neuron need to be updated, but its neighbors' weight need to be updated too. But how much its neighbors need to be updated determined by the neighborhood function. In this code, we are going to use the Gaussian function as neighborhood function. So we click new, and we type in the function, and my Gaussian equal to, give a name, let's get EIJHBOR neighborhood function, winner index, so here we define the neighborhood function. We're using a Gaussian function as an example. In this function, there are 3 input and 1 output. The input is the winner index, the radix, the NN. So let's explain one by one. For a Gaussian function, we know there are 2 variables. One is the mean, another one is the standard deviation. So here, the winner index, that could be used as the mean of the Gaussian function, and the radix could be the standard deviation of the Gaussian function. And the output, of course, is the Gaussian function. And here, the first step, we need to define at least one neuron need to be updated. So this step can guarantee at least one neuron need to be updated. What's the meaning of radix we will introduce later. So here, that could be viewed as the standard deviation of the Gaussian function only. So next step, we calculate the distance between the winner neuron to other neurons. So here we can see this is find the absolute value between the winner index and all other neurons. So this is how many. This is the size, how many neurons total, and using that one to minus all others. And then we can decide if the distance is too large. We can choose the minimum value of delta S and the size n1 and minus delta S. Now we have the distance and we know the standard deviation. Now we can calculate the Bayes-Gaussian function. So here, as we know, basically the Gaussian function is an exponential function, and here this is the mean of the x minus the center one, that's the winner index, and then square. Here, please remember this when using the dot square, because the this is a vector instead of variable. And radix is the standard deviation. That basically tells you how wide you want your Gaussian function. So here you click the save. The function will be automatically saved as the getting neighborhood functions, and click save. It's back to the main function, and we copy this to here. Now the winner index is comes from previous command. The n is from the definition. We need to change the radix. That's as the fixed n and over, for example, 8. So this determines how wide you want to change your neighborhood. So here about the neighborhood functions, there are two things we need to know. The first one is the my Gaussian function at the winner index has the value that's equal to 1. At other location, the value is between 0 and 1. With closer to the winner index, the value is higher. With farther from the index, that's equal to that's lower. Let's give a try and copy the code here, paste here, and then give I equal to 1. I equal to 1. And let's see what's the winner index. That's equal to 4210. And my Gaussian 4210. That's pretty close to 1. And with on both sides, closer has a relatively larger value and the farther has relatively smaller value. Let's give, like, for example, give 2220. The value is lower compared to 10, and give, like, for example, 43. The value is even lower, and give, like, 4,000, 5,000, even lower. Okay, this is the first thing we need to know. If we plot the my Gaussian function, Oh, let's close. Oh, and plot it. We can see, let's grid it. At the center one, here will be the 4210. On both sides, the value is going to decrease. That's the first thing we need to know. Second is, we can zoom out. So second thing is, with different input city, the Gaussian shape will be changed, is going to change. Let's give another try. Let's see I equal to 2. And then we run this. Now we get new Gaussian functions. And in this code, we make it hold on. And then plot my Gaussian function with different color. This red color. Now you can see the shape still same, but the totally shift. If you give another try, you can see you get another Gaussian function. Okay, this is two things we need to know about the Gaussian function. Now we got the neighborhood function, and the next step is updating all the neurons. Let's type in update neurons. Here we're using this one to update the neurons. And here LR is the learning rate. And the Gaussian, my Gaussian is the Gaussian member function, Gaussian neighborhood function. And city is the randomly selected city. And here we want the learning rate gradually decrease. 7. As we introduced in earlier videos, we know if the learning rate is too small, the convergence speed is too slow. On the other hand, if the learning rate is too big, it will never converge. Therefore, we're using the LR equal to LR multiplied with a number to control the learning rate. We also want the number of upgraded neighbors gradually decrease too. Equal to Now we finish the major part of the code. And here we'd like to take a look what's the training result. And let's show the result. So first, let's change the iteration times equal to a very large value. And then next step is we can output the result. Here we want the every 500 iteration we have one output. This is controls output figure. And give it the figure location. Oh no. And now I control its position. So here you can change this sentence according to your screen size. I have pretty big screen, so I make this one is relatively large. And then give it a paper mode. Here you can check online how to control these figures. This is not the focus of this slides or this video. We don't want to talk about more about this. Plot the x-axis. No. So x-axis and y-y. That is the city's latitude and longitude. And we give a line with 2, 3. We hold on. That is the neuron output. Each time, since for each iteration, we need to upgrade the neuron. So this is the upgrade neuron from each time. This is to control your output. You want the font size a little bit bigger. And make the font weight is bold. Then give a title. That's to mark what the iteration is output. Iteration equal to, that is the current iteration. And here, since we want to see the difference, we just pause and then close all and end. So far, we finished all the code, and here we want to take a look what the result looks like. Let's click the run. Okay, this is iteration at 500. So here the red dots are the cities from the city, all the cities, red dots, and the blue line is the route you're going to do, the salesman going to do. This is just from very beginning, and it's definitely not very good because they're missing a lot of cities. Now try the second iteration, second time. So after 1,000 times iteration, we can see it's better. It can cover more cities. 150, 1,500 is much better. You can see compared to 500 and 1,000 is much better. 2,000. Oh, it's good. 2,500. 3,000. 3,500. 4,000. See, it's almost visit all the cities along the curve using the only one trip. 4,500. 5,000. 5,500. Keep going, keep going. You can see even just we finish the 9,500. This already give us the optimal route, which lets the salesman visit all the cities, but for each city only visit once. Here in the code we set iteration is 27,000. That's a really big number. We can see only at 9,500 it can give us really decent results. Maybe a few of them are missing, but I didn't see it. It's very, very good. You can see now it's really, really good. Just finish our goal. I think we can stop here. Go back, look at our code. This code is really, really, really simple. It's only less than 100 lines, and plus we have two functions. One is select the winner, another one is get neighbors. So pretty simple code, but it's really good approach to solve this very difficult problem. Okay, that is how do we apply the SOM to solve the salesman traveling problem.